Okay, welcome everyone to this joint keynote of the SLE and GPCE conferences. It's my pleasure to introduce Julia Lawall to you. Julia's working for INRIA in Paris, and she has kindly agreed to give this keynote on Coccinelle, which is, of course, a program analysis and transformation tool for C. It's well known. I also don't... Yeah, please. I also don't think Julia needs a lot of introduction. She has published at both of our conferences in the past. She has also served as a programming committee member in the past. And I'm really looking forward to hear more about the recent advances in Coccinelle, this great program matching and transformation tool for C, which is robust enough to even support collateral evolutions of the Linux kernel. So Julia, the floor is all yours, and please join me in welcoming her.
Okay, thank you. So thank you to the SLE organizers and the GPCE organizers for inviting me, and welcome to the SLE people who have come down here to visit the GPCE room. So I will talk about Coccinelle, impact, and internals. So we start out by thinking about the software lifecycle. So you have some wonderful idea of some software you'd like to make, and then you make some quick and dirty implementation. But over time, maybe some people actually, you make some publicity, people like your software, they start to use it, they ask for new features, so then your code starts to get bigger and bigger with the new features. They might find bugs. There's some bugs for you. And then when your software is really successful, then people start to attack it. That's how you know you've really arrived. And so then you have to deal with these problems. And so your software, each time we discover we need more features, we find more bugs, and so on, your software gets bigger and bigger. So basically, in general, as software matures, you need to keep rethinking your design decisions. So you start out with something small, quick to implement, if you have to evolve it, these new design decisions induce pervasive changes. So these changes are easy to make when the software is small. You can, for example, completely change some data types, do some reorganizations, but over time your software gets bigger and bigger, and this gets harder and harder. So actually our motivating example is going to be the Linux kernel. Linux kernel in 1994 was around 100,000 lines of code, and it's 23 million lines of code today. So you can imagine that changes that were easy to make when we had only 100,000, or moderately easy to make when we had only 100,000 lines, when it gets so much bigger, are going to be tedious, tiresome, error-prone, and overall discouraging. So the developer may be discouraged from actually modifying their code just because it's going to be so much work. So basically the question then is, as the software is growing, how do we ensure that it continues to be possible to maintain it? So an easy thing to do in general, you may have some libraries in your software, and then you have the clients of those libraries. So updating the library, you think of some new clever implementation, you need to think of some new parameter that would be actually provide you with lots of information to make a more efficient implementation, so on. All of these things are quite easy to do. But then the problem is, like, how many users of this library are there? And it depends on your software. The users may be actually internal to the software project, or they may be external. You may have some kind of modular system where people can load things in dynamically, and all of those users are going to have to know about all of these changes that you need as well. And so this problem just gets bigger and bigger as your software gets bigger and bigger. And so ultimately, developers may think, oh, this data type would be safer, easier to use, more secure, and so on, but it's going to require me to go and search through thousands of lines of code to find the places to update, and so that would be, maybe we just won't bother. So the target of our work, maintenance of large critical software, like C code, specifically the Linux kernel. Coccinelle today is used for other kinds of C projects, and you will see at the very end of the talk that we're actually starting to target some other languages, but it's most developed for C code. So I'm going to start by giving some examples. So the first one is the transformation from init timer to setup timer. So in the Linux kernel, timers are very important. We need to initialize them. Initializing the timer, you create some data structure. You call some init timer function, but then you also need to provide some extra information. One of them is the function that should be invoked when the timer expires, and one of them is the data that should be passed to that function. So you might think a timer, you need to know when that timer should expire as well, but actually these timers are reusable things, and each time you say when it should expire. So it's actually just the data and the function that are important. And so we end up with code that looks like this, where we have the init timer call, and then we have there's like 3 operations that we need to do this timer initialization. So 3 operations, it's a bit tedious, all that typing, and also these operations might be kind of scattered and reorganized in different ways. And so someone had the clever idea. They see we do this thing over and over again, and so we may as well just have one function that does the whole thing at once. So there was a function called setup timer that was introduced. I think I have the dates here. So we go from version 1.2 to version 2.6. This is a really huge amount of time ago, like nearly almost 20 years ago that setup timer was introduced. It's more concise, it's more uniform, and for some reason that I don't completely understand, it's also more secure, just because I guess we have everything being defined at the same time. And so then we can look at the history of the Linux kernel and see how these things have been used. So here is where setup timer was introduced. Somebody made a few changes. There's like some effort here. We have a drop in the number of init timers. We have an increase in the number of setup timers. But that effort didn't really go on very long. And then the number of init timers creep up as people are adding in more and more code, maybe more device drivers, maybe more file systems, whatever different things that need timers. And actually, typically in the Linux kernel, people may copy some code that exists and just adapt it to their needs. And so they're going to end up replicating this out-of-date code. People were adding more setup timers at the same time. Things sort of plateau. Again, people start making an effort again. The number of setup timers increase. And then here at the very end, in 2017, somebody made the big effort to say, okay, we're just going to stop doing this, and got rid of all of the init timers. But you can see it took a huge amount of time. It's more than 10 years that we took to get to that point. So another example is KZalloc and dev-mkzalloc. So the Linux kernel is a self-contained object, so it defines its own memory allocation functions. KZalloc, it's just like malloc, except it is at the kernel level, and the Z means that it zeros the data. It's not very important. The important thing is that it's C, there's no managed memory, so whenever we do a malloc, we have to actually do a free afterwards. And frees can be forgotten, and we get memory leaks, a traditional story. So someone observed that actually there's sometimes when we actually know when we want to free the memory, and we can do that automatically. So basically a device driver, we have a device, and a device driver is the thing that's going to manage the interaction with that device. And typically managing that interaction requires some data. So you initialize the device driver, you allocate some data, and then that data is going to live all the way until you remove the device driver. So there is a case where we know actually the lifetime, and what happens is that when you do some kind of allocation with this dev-mkzalloc function, that allocation, a pointer to that allocation gets stored with the device, and then when you free the device, then you can free all of the data that's been stored with it. So that's something that simplifies the code a lot. You don't have those frees. You can also get rid of some kind of error handling code and so on. So that's fine. And so again, we can look at the history of how this has been used. It seems like a nice feature in the sense that it simplifies the code a lot, and it also removes memory leaks. But you can see here, it was introduced in 2008, and it took a long time somehow for it to take off. Like, it wasn't really visible. People didn't really understand how they should use it. It existed, but just in a few files. And so eventually, somehow it got some publicity, and then it started going. But it would have been nice if the developer here could have made all of those changes that are possible initially. Of course, we can't completely get rid of the original allocation functions because the kernel doesn't use allocation only in device drivers, as he uses it for other purposes, but maybe we have now reached more or less optimal solution where it is being used everywhere it needs to be used. The last example I'm going to show, this has to do with reference counts. So again, it's some kind of memory management issue. You use a get when you want to take a pointer that's going to point to some object, and then you have a put when you're done using it, and if everybody who is using it has done their puts, then the object gets free. And so it's again, get is something you have to do. It's actually kind of built into all of the functions that allow you to access certain types of data. But put, who really cares about put? We don't get any information from it, and so they tend to be forgotten. And actually in Linux kernel, they have defined some iterators that iterate over a list of these objects, and on each iteration, it does a get and a put. So then you can actually iterate over the object without actually thinking about the reference counts. The code becomes very simple, very nice, except for the fact that when you jump out of the loop, then it will only do the get and will forget to do the loop is not going to automatically do the put for you. Because the iterator is just a macro and it doesn't actually process in any way the body. So then the developer has to remember whenever there's a jump to put in the puts. So this is, again, something that people often forget, again, leading to memory leaks. So here are the leaks that have been detected over time. So this is just like a pure bug finding situation. There's no new API that we want to move to. But you can see the same kind of pattern. People show some enthusiasm for the problem for a while, and then here they show some enthusiasm for the problem. Lots of them go away. Then they get tired. Lots of them come back. More enthusiasm, more tired, more enthusiasm. So now they've been kind of killed off, and so maybe it starts to be well known that you need to put these puts. But in general, we can see that it's just hard to do these kind of pervasive changes in a huge piece of software. I would note that another particular aspect of the Linux kernel, it has a huge number of maintainers. There are different parts of the kernel. Some of these maintainers work hard, some of them are busy with other things, and so it may take different amounts of time for proposed commits to actually get integrated into the code. So that kind of slows down and kind of discourages people also from doing these tree-wide changes. But Coccinelle doesn't help with that. Coccinelle is just going to help you make the change. So Coccinelle to the rescue. So what is Coccinelle? Coccinelle is a pattern-based tool for matching and transforming C code. So at the time that we started developing it, which was like 2005, somehow the latest big thing in C code program transformation was SIL, which comes from George Nekula. SIL was very nice in that it gave you a parser. It also gave you a visitor for the trees that you had parsed, and it gave you some analyses such as alias analysis and so on. But the hard thing about it was that the C language is really complicated. It has lots of different constructors, and if you wanted to use SIL, you had to think about things at the AST level. And so you had to spend a huge amount of time like saying, okay, I want to match an integer. Okay, so what's an integer? It's like an expression, it's a constant, it's a 64-bit integer typed expression, and then finally you can get down to that value 3, which is the thing that you're looking for. So it required a lot of like general familiarity with the concept of an AST and the kind of terms that are used in programming languages to reason about code. So us, as people fairly knowledgeable about program analysis, found it kind of tedious to use. So we didn't really think this was a tool that Linux kernel developers were going to want to use to write generic transformations. So that's why we took the opposite approach. Our idea was to actually focus on a notation that Linux kernel developers are familiar with, which is patches. So a patch is like a fragment of code. It removes some lines. It adds some other lines. I'm sure today everybody's using Git. You run git log -p. You see the patches, the changes that have happened in your software. So we want to focus on patches, but patches are very specific to a particular part of the code. And so we wanted to make them more generic, and so we called them semantic patches. So the semantic, I mean, that's like a little bit of exaggeration. There's not that much semantics, but we do know, the semantic patch language does know about types, and it does know about control flow. Like when you have a loop, then you go around the loop. When you have an if, you branch it the different directions and so on. So basically, it's basically a domain-specific language for writing program transformations. Our goal, like any domain-specific language, is to fit with the habits of our users. And so in this case, our users are Linux programmers. We want to exploit the knowledge that they have about their code. In general, developers know a lot about their code, like some kind of implicit invariance and so on. We're not aiming for like a fully proved program transformation system. The tool is not trying to discover invariants or semantic properties or anything like that. The goal is to allow the software developer to express the knowledge that they have and make transformations accordingly. So here's the idea. So we see semantic patches. So basically we have code fragments, and they're annotated with minus for the lines that we want to remove, and plus for the lines that we want to add. And I mean, like basically like ordinary patches, but we want to be a bit more abstract. And so we're independent of white space, comments, line numbers, new lines, and so on. And we also have a notion of metavariables, and the metavariables can match maybe any expression, any type, any statement, any integer typed expression. There's a huge range today of metavariables that you can match. So here's a typical example. Here it's like basically it's at, which is like the patch notation. And then we have another at. So in patches, it's at and line numbers and at. And so what we do instead is at and then metavariable declarations and then at. Some people thought this little joke was a bit silly, but we stuck with it anyway. So you define your metavariables, and then you think about what code transformations you want to perform. So here, this is a very trivial example. We have some random function called f, and maybe it's often called with 0 as the first argument. It has 2 arguments. For some reason, we feel like if it has 0 as the first argument, then we have a special version called f0 that we would like to call. So we would like to go over our entire code base and find all the calls to f that have a 0 as the first argument, and we just replace them by a call to f0, and then we just want to leave the second argument the way it is. So this is a little semantic patch. Then you can run spatch, that's the name for the tool of Coccinelle, over your code base with this semantic patch, and then you'll get a patch out. Actually, by default, Coccinelle doesn't transform the code for you, although there's like an in-place option. By default, it gives you a patch. You might like it, you might not like it. You can even remove some bits of it that you don't like before you apply it to your code. So basically, it's trying to automate things for you. It's a programming language. It allows you to express whatever you want. What you want to express might be good, it might be bad. That's the part we don't take responsibility for. We just expect that, like any kinds of transformations for your code or any kind of contribution that you make to any software project, people should be looking at the code afterwards. But it's more reliable in the sense that things are done in the way that you have expressed that they should be done. So we're going to look in more detail at a real example, which is the init timer one that I talked about before. So kind of a typical way to make a semantic patch is you can start with a real patch and then abstract over it. Then you can try it out. You can see that it's actually not taking into account everything it needs to take into account. Then you can update it a bit. We kind of rely on the fact that it's very close to the code, it's very readable, and so it's easy to evolve, and then ultimately you get something that's at least very close to what you want. So here we have a patch from some random driver, and this shows basically the kinds of things I talked about before. We have the init timer call, we have the initialization of the data field, we have the initialization of the function field. And as I mentioned before, the person didn't change this expires field because that's not part of the initialization process. And we replaced the whole thing by setup timer. So this is like when you look at it, you can kind of understand, if someone gave this to you as an example of the change, you would kind of understand this as an example. But if you give it to Coccinelle or some kind of patch application tool, it's only going to work at one specific place in the code where we have these specific values. So what we need to do is raise the level of abstraction so that it can apply everywhere. So the first step is to take the code that we have and remove the bits we don't care about. So as I said, we don't care about the expires initialization, so we remove that. And when you remove something, it's like there's kind of this knowledge that some stuff could appear in that place. And so we can use ... to say that some stuff can appear in that place, but we're going to make our changes in the other places. So that's kind of the intuitive way. If we were sharing this information with your colleague on a napkin about how we make this transformation, you'd probably write ... as well. So that was our idea, but actually ... has a meaning a semantic meaning in Coccinelle, which is that the thing that's matched beforehand, so we have this init timer, and then ... means that we go over all the control flow paths and we be sure that there's a initialization of the data field afterwards. So it's checking that things are actually consistent in some way. So the next thing is the subterms. We saw an example of metavariables before, but the point is that we're not interested in specifically NS timer or specifically this value or specifically this value. We don't really care what any of those things are. So we can take them and we can abstract over them using some metavariables. So I made metavariables, whatever you like to call them, timer, function argument, data argument, and then we end up with this as the semantic patch. So basically, we match some things in the removed code, and then we use those things that we match in order to construct some added code. And you can also use these, oh yeah, here we even do that. You can use a metavariable in multiple places. So here it's timer, here's timer, here's timer, and those are all going to have to be consistent. This allows, among other things, we can have some kind of nested, we can be matching and transforming multiple timer initializations that are interleaved with each other, and Coccinelle will take care of doing everything the right way. So another thing, just kind of experience shows that it's useful. I don't know, we didn't see any constraints on having init timer and the initialization of the data field right after each other, so between the data and function, there could be other code as well. And so now we have our semantic patch, and we can apply it to the Linux kernel. So actually, to test this one, I didn't apply to the Linux kernel. I went through the entire history of the Linux kernel, because people added them and removed them and so on. So I went through the entire history. I got all the different unique init timer calls, and then I made a big data set, and I just tested it on that. So we have 600 files over time have used init timer. There were in total around 800 calls, and our patch updates 300 of them. So it might be a bit disappointing because 300 is a lot less than 800. It seems like we still have a lot of work to do. On the other hand, 300 is still 300. I mean, it's a lot of searching for different lines and updating and a lot of tediousness. So as just right now, does anyone have any questions? Yes, Eric.
I have a microphone. Hi, I'm Eric Benny. Can you go back to slide 18, just this little bit of code? Yeah, so this example moves the use of function arg and data arg up over some elided code. Mm-hmm. And so what if data arg and function arg are computed by the elided code? Isn't this transformation incorrect?
Yes, so that's a good point. So there's two options. One of them is that you can put some when things here. And the when things might say when there's no initialization of data arg or function arg. Another option, of course, would be just we don't have to put the setup timer call here. We could put the setup timer call at the end here, and that would solve the problem in another way. I think the reason why I made the semantic patch in this way is that seemed to be what human developers had mostly done, which was to put the thing back up here. So, I mean, it's a good point. You write your semantic patch however you want, and you can, as I mentioned, you can put some when constraints on these things to ensure that there's no updates of them. But that's all the guarantees that you get, yeah. So there was another question?
Yeah, thank you. Can you go back to the next slide, please? Yeah, so you mentioned that you're able to update like 300. It's very impressive, but is there like a common pattern where you see for the ones that it did not update, right? So is there like a particular, like some common
Yeah, so that's, sorry,
causes,
that's what's coming just right afterwards.
Yeah,
So,
You might also be getting to this, but is there a way to specify you don't care what order those statements are in?
yeah, so actually, so here we go, just going back here. So here we have ... And when we first made Coccinelle, we thought that people would often like to do what you just suggested. And so we made I don't know, there was like circle, 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 and star, star, star. And the fact that I do not remember which one does what you're saying suggests that we found it really not useful. So in this particular case, it would actually, I mean, if we put circle, circle, circle here, then maybe we could have it a more concise representation. But it seems like in most of the things that we ever wanted to do, we didn't want that feature. And so those two features actually never got really implemented. They got parsed, but nothing more than that. And so they just got removed at some point.
Okay, thank you.
So, yeah, so I mean, you have both gone in this direction of like, obviously, maybe it's not very important the order in which we define data and function. And indeed, we can make our change, we can get our patch, we can apply it to our code, and then we can grab what are the init timers that are still remaining, and we may quickly see this one, and then we can say, oh yeah, okay, there's no real reason to put data before function, we could do function before data. So now we want to extend our semantic patch to do that. So it's basically, one option, I mean, there's many options, you can make multiple rules that do different things. And you can also just kind of combine them in this way, which seems sort of natural in this case since they're so closely related. So what we have basically in a traditional patch syntax, the column 0 is important. And so we allow some other little extensions to the patch syntax in column 0. This means parentheses. So the pipe means either this or that. And so then we just have our different options. We also have another extension, which is and, if you wanted to match both this and that. It seems a bit strange. I don't think that could possibly work in this case. But there's some other cases where you want to describe the same thing in two different ways, and then and can also be useful. So now we are up to 656. So this is about 3/4 of the calls. Pushed it a bit further. I'm not going to go into all the details. We can see sometimes people put the initialization of the function and the data before the call to init timer. They're just, those are just random data structure initializations. There's no dependency between them. Sometimes there's no initialization of the data because they want it to be 0, and actually the structure is just initialized with zeros already. And sometimes Coccinelle times out for some reason. You can specify whatever timeout you want, and then it will fail. It will report to you that there was a timeout on this file. You can try to deal with the problem by yourself. So in the end, we have 6 rules, and we have 68 lines of transformation code. So it's a little bit, it's not completely trivial anymore, but maybe it's still fairly readable, especially since the things are very similar to each other. And at this point, we get to 808 out of the 828 different calls. And the other calls are not very amenable to optimization. Like people initialize those function in data fields in some other function. Coccinelle actually only works on one function at a time. Like you have one rule and it's applied to each function. You might have another rule and then it will be applied to each function in the result. So there's no interprocedural analysis. There's ways to encode it, but it's not really the natural thing to do. So our point of view is the Linux kernel tends to have fairly large functions, and so somehow a function is some level of abstraction, and so most of the things you want to do will just fit inside of one function. So overall, we've seen the rules are small, readable, and they can transform lots of code. It's reliable in the sense that at least we are figuring out the boundaries of an identifier. People try to do things with regular expressions, but they might forget to make their regular expression really robust. So there's no chance that we're going to change the calls to other things that end in init timer. And a much more important benefit in the context of Linux kernel is that we check all the files systematically. So Coccinelle is completely independent of the configuration. The Linux kernel is really a product line. There's a configuration file. You say, are you x86? Are you ARM? And then different code is included or it's dropped. So we completely ignore that and we just try to parse the code as we see it. And in this way, you can change all of the Linux kernel, all 23 million lines of code, and not just that from a specific variant. And so we've also seen this standard process of iterative development where you write the rule, you apply Coccinelle, you see what happened, you write the rule, adjust the rule somehow, and eventually you're pretty happy with the result. There may be a few places to change by hand, and then you can just, it's always a trade-off. Do you automate or do you just fix it by hand? So this is like Linux kernel developers have reported to us or like asked us, like, they say, I do this, is this the right thing to do? So I think it's the right thing to do. Yeah, Vadim?
So does it ever happen that you need to have several rules that sort of help each other out and then you need to run them together rather than focus on one rule and only do that?
Yeah, so definitely. We will see later on in the talk, but with Coccinelle, you can have a whole series of rules, and they can inherit information from each other. And so then you can have one rule that, for example, a kind of classic example is you have a structure with some function pointers in it, and you want to do some transformation on the function that is stored in a particular field in that structure. So in the typical names in Linux kernel are like probe for initialization, remove for removing something. But the names of the functions might be some random thing, init my device or something like that, without the word probe in it. So you can't really use regular expressions to find all the functions that you want. So you can match against this structure to find the names of your functions, and then you can make another rule that's going to use the name of the function that you found, and will go and actually work on the definition. So that gives you sort of a very limited sense of interproceduralness in that you can collect things from anywhere in the file and then make more rules that use that information on other functions.
And the rules can collaborate?
Yes, the rules can collaborate, yes. But it's not, we only go like this. We don't go backwards ever. I mean, there is a way for it going backwards, but it's kind of awkward intentionally somehow. The idea is just to do more simple things that go like that. I think there was another question in the back.
How do you deal with nested constructs? Because then you have because it's lexical matching, you have the parenthesis problem, and if you have, let's say, an if block, if-else block, and it seems to me that you're matching the first case that occurs, but that might not be the right choice. If you have then a closing parenthesis, so ... a closing parenthesis, you might have to use the last parenthesis for the match and not an earlier one. How's that? Or you might have also nested.
So are you talking
function
about
calls.
parentheses like braces explicitly?
Whatever,
Yeah,
anything
so
which occurred in paired fashion.
I mean, we are not doing, there's like several answers. In the case of parentheses, parentheses occur inside expressions, and our matching is based on ASTs, so naturally the parentheses will match up in the right places. Then there's also the question of braces. Those are not inside expressions. They're going to be like, braces are going to be separate, and we have a control flow graph. They're going to be separate entries in the control flow graph. And actually, internally, every brace has a number associated with it. So I'm brace 27, and then it will, if you match brace 27, and then your semantic patch has matching braces indicated in it, then the closing one will look for brace 27. And it's actually quite interesting because we are doing, our matching is over control flow patterns through the function. And so there may be returns, and there may actually be many occurrences of brace 27 somehow. Each return is going to get filled in with all of the braces that, like returns are a path that cause you to leave the function. And so all those braces that led to the return will get matched implicitly afterwards somehow. I think there was a question in the back. No? Okay.
Just a
Good.
quick clarification question. So as you mentioned, this is not in place update, right? So say if you find this like 500 bugs or call sites, so does it generate like one semantic patch where you say, well, I want to replace all those 500 call sites, or it's like it actually requires programmers to go through every single one to decide whether they want to apply the patch to individual sites?
So you run Coccinelle on your entire software if you like. I mean, you can also run it on just one file. You can do whatever you want. And it makes the changes for all the files that it finds that are relevant. It produces one patch. Patch is a textual object. So the idea I had was that like the developer can look through that patch and say, oh, this change was completely off for some reason, and just remove those lines of the patch. Or, I mean, in general, one should look through the patch before applying it. But then there's also the option for people who are very enthusiastic about Git, is you can do in place, and then it will just change your code. And then if you can do some kind of Git add magic and only add the parts that you like or something like that. So either way. Was there any question farther in the back? I don't know. I thought there was, but okay. So I just have some other examples of things that Linux kernel developers, so not me at all, have done. So like removing unused function argument, eliminating a redundant field in a data structure. These are mostly impressive in the sense that they affect lots of files, and it would be very tiresome for people to have to go and find all those files and make the changes. The last one is a lot more complex. It's like we have a special argument from a certain kind of handler. So we have to go find those handlers. We have to find the argument. And in some cases, the argument is actually being used in the code. So we have like, I don't know, there's almost 200 files that are affected, but there may be 500 uses of definitions of these handlers for different purposes. Some of them are still using the argument. Those that are using the argument, you have to update the uses. I think introduce a new local variable declaration that will provide the definition of the thing. And the other ones that are not using it, we just remove it. And this is also something that heavily is dependent on configuration. You can imagine there's interrupts across the entire Linux kernel, so ARM code, Linux, x86 code, and so on. The person who started doing this transformation by hand first did it kind of a compile and fix up the bugs option. So you just change the prototype, then you try to compile, and GCC or whatever will tell you, oh, this function is now taking too many arguments. So then he would go and fix all of those. But he was completely missing hundreds of occurrences where they were for other architectures than what he was trying out. So this is something where Coccinelle was really useful in many different ways. So now I'm going to talk, we're done with the examples part. Now I'm going to talk about sort of the internals. How does it work? I'm mostly go over this. Basically, we have our C code as input. We have our semantic patch as input. The C code is parsed, and then the parsing is converted to a control flow graph. The control flow graph is being used to implement the ... so that we can get all the control flow paths through the function, ensure they're consistent, and so on. The semantic patch is converted into a CTL formula. So basically, the idea is whenever we have ... in the semantic patch, that's going to turn into a U, which is like search over a path. And so then we take our CTL formulas and we use some variant of normal CTL model checking to apply the formula to the graph. And the formula may match at many different places. If there is a match, then we do the associated transformation. There has to be a complete match. There's no like partial matches or something like that. If we have a complete match, then we do a transformation. So basically we start out, we might have a file with 5 functions, and we might have a semantic patch with 2 rules. We take the first rule, we apply it to each of those 5 functions, and then we move on to the next rule. and we run the next rule on the output of the processing of the first 5 functions, and so on. So if you're interested in the model checking aspect, that was described in detail in a paper in POPL 2009. Since that has already been published, that's not what I'm going to talk about. I'm going to talk about some things that have not received much, sort of conference attention before. So specifically, I'm going to talk about the processing of the C code, so the whole parsing process mainly. I'm going to talk about how we handle multiple rules and what was asked about before. How do we transfer information from one rule to another one? And also about the code generation process. Our goal is that any code that is not actually modified by the transformation should look exactly the same as it did in the original source file. We're going for source-to-source transformations. We want to have an impact on the Linux kernel. Linux kernel is not going to be happy if we pretty print everything with, for example, this is like an inside Linux kernel joke, but I mean, we really like tabs in the Linux kernel. We don't want 2 spaces or something like that for all our indentation. I'll start out with the processing of C code. So we want to support real Linux kernel source code, and this was like a goal from the very beginning of the project. So we never had any kind of like toy parser for C. We always, from the very first publication, the very first work on it, we had a parser that we iterated over until it came to like 99% of the Linux kernel. As I said, we have our own parser. So remember, this was like 2005 also, so there was no like LLVM yet. There was not that much infrastructure that was very useful for us. I don't know if we would make the same decisions today or not, but today it's not really practical to switch to some kind of more modern infrastructure because in our parser, in our AST, we have exactly the information that we want. And so some other tool might have information, but not in exactly the same format and so on. So it would cause problems. So our parser, the one interesting thing about our parser is it keeps all the information about spaces and comments. That's all going to be essential to regenerating the code. And the other interesting aspect is it doesn't use the preprocessor at all. So the parser starts out by attacking the code exactly as it is. So this is a great feature for program transformation. For if people are writing rules, they see the code. In C, there's nothing special to indicate that this is a macro. It just looks like a function call. It looks like a variable reference. So they just see the code, it looks this way, and then they write the rule according to how the code looks without thinking about whether it's a macro or not. Another huge advantage is in the Linux kernel, macros are mostly defined in header files. Since we don't care about the definitions of macros, we don't have to include those header files. You could object that the header files often contain a lot of type information that we might find to be useful. So we have some command line options that will let you include, you can include to different levels. So you might include only the header files that are actually mentioned in the file, or you might recursively include the header files. There's also an option that is like include headers for types. So then it will only pick up the type information and throw away all the other stuff that you're not so interested in. But header files are huge. They often are difficult to parse, and so not including them is a huge performance benefit. And as I mentioned, we just work on one function at a time, so we make our control flow graphs just intra-procedurally. So basically, we have one node for each atomic thing, statement, whatever, in the control flow graph, and it describes how we go around ifs and how we go around loops and so on. So I'll go into a little bit more detail about the parsing. So we parse basically one function at a time, or one top-level object at a time. That might succeed, that might fail. If it succeeds, then the semantic patch rule will get applied to that thing. If it fails, we just move on to the next thing. So by default, we don't give any feedback about whether parsing succeeded or failed. There's a command line option if you want that feedback, but typically a semantic patch will be working on code inside of functions. In a Linux kernel, the code inside of functions is usually nicely written. It might be using macros, but they will look like function calls. Macros, on the other hand, may be very strange. And so if you were getting warnings about compiler errors, then it would be complaining about all those macro definitions. You don't want to see that because you don't care. So somehow things work very smoothly because of that. For parsing each possible thing, we make 4 attempts. So the first attempt just looks at the definition, tokens in the definition, tries to parse them. There may be some things that are just impossible to parse. And so then it starts looking around at local, maybe macros defined in the same file, macros defined. You can actually give a configuration file with your favorite macros, so it can look in there. And it does a little bit more macro expansion to try to save the situation. But remember that, you can give, if you have some other software project that Coccinelle is not really well tuned for, you can give some macro definitions of your own. Usually that will let you go from parsing about 20% of your code to about 80% of the code. Usually there's just a few macro definitions that are really key to that. But in general, expanding macros is a bad thing for this kind of source-to-source transformation, because then you end up with some region of the code that has 2 possible representations. And then it's not really clear, what if your rule matches the expanded part, it doesn't match the original part, what should you do? How should you manage that? What if it manages stuff on the boundary between the original code and the expanded code? So since we don't really have good answers for any of that, when we expand macros, you're no longer allowed to transform the code. If you have a function and you're saying, just let's remove the whole function, and if there was some macro expansion in there, then it's willing to remove those tokens. But actually, replacements, it doesn't do. So expanding macros unnecessarily has a consequence, and so we try to do that as little as possible, just to be able to parse the function. And then we also have this system of parsing hacks, which was described in a paper in CC 2009. Basically, we have traditionally you have your lexer and your parser. We have a YAC-based parser. And you think of them as just kind of working together and, some kind of indissociable object. But actually, our lexer, we run the lexer first, and then we do all kinds of funny look-ahead things among the tokens. We re-encode some tokens to make things unambiguous, and then we ship the whole token stream off to the parser. So the most traditional example is this. This is like an ambiguity in the C language. If you don't have type-def information, remember we don't have header files, so we don't have much type-def information. If you see X times Y semicolon, okay, so we think Linux kernel programmers are, knowledgeable people, and so they don't do completely useless things. So a multiplication at top level is a completely useless thing. So it must be that this X is a type. This must be a pointer declaration. And so actually now that we have inferred that this is a type, then we can propagate that information to the parsing of the rest of the file, and we can actually find some type defs sort of on the fly and get better parsing elsewhere as well. And so with all these hacks and different things, we can parse over 99% of the lines in the Linux kernel. Okay, so the second issue is when we have multiple rules, how do they communicate with each other? So this is a completely toy example. It's a very useful feature in practice, but things might get more complex. Basically, we have 4 rules here. We have each one is going to remove some function calls. And you see, this time I've given each of the rules a name. So this is rule 1, rule 2, rule 3, rule 4. And here we have some metavariables, but they're not fresh new metavariables. We're inheriting A and B from rule 1. And here we're also inheriting A from rule 1. Z is going to be a new metavariable. Here we're inheriting B from rule 1, and we're inheriting Z from rule 3. So you can define metavariables in various places, and then you can merge them together and have other rules that collect all that information and do things with it. So we have a fairly silly program here. Here we're doing F, G, and H, so I've made little function calls to F, G, and H. It's not meant to be an interesting example. So basically what happens is that matching these different rules creates environments. For example, we'll see that matching this rule here against this code will create 3 separate environments. And we keep those environments separate, and we just propagate those environments from the matching process of one rule to the next one. So basically, we have a big tree. The first rule establishes some environments, and then the next rule is going to be applied to, the first rule is applied one time to this function to all the places where it goes, and the next rule here, because there's 3 different matches for this one, this rule will be applied 3 times. And so things can get bigger and bigger. Internally, we have some optimizations, which I will show in the successive slides, but the idea is the user should not have to think about whether these environments are being merged and so on. They should just think of them as being complete objects somehow. So here's our rule, our first rule. Here's a little bit of our code. We start out with an empty environment because we haven't done anything yet. We apply rule 1, and as I said, we can apply rule 1 at 3 different places, and things come out in 3 different ways. We get A being 3 from the first call, B being 4, A being 1, B being 4, and 1 and 2. So we have 3 separate environments, and they are going to be passed into the next rule. The next rule is actually just inheriting all of its metavariables from the previous rule. So this rule will be applied 3 times, once according to this environment, once according to this environment, and once according to this environment. And so we can check GAB for the first environment, 3 and 4. Okay, so we have a call here for that will match that one. For 1 and 4, so that one actually doesn't match anywhere. And for 1 and 2, that one will match here. So these 2 will be changed, and this one will just remain in the program. So our next time, the next rule, so we can look at rule 3, and rule 3 inherits, again, it inherits the A that was defined in R1, but it doesn't inherit B, and it defines another new metavariable. So I've kind of indicated that here. So we have the information that comes in from before is that A can either be 3 or A can be 1. There's no need to work on this environment and this environment because they have the same metavariable, the same values for the metavariable A. So there's no point to apply this rule 2 times for these 2 different complete environments. But we don't want to completely forget B because B could be inherited, or actually, I mean, an analysis is done in the beginning, in the parsing of the semantic patch, to figure out that B is actually used in the future. And so we need to remember the values of B even though we're not using them in this match. So now we have H. So we can see our 3 calls to H. We have our 2 environments that we need to try. A equals 3. So that will match this one. It will produce A is 3 and Z is 1. And now we have another one, A is 1. And now we have 2 possible matches for that one. A can be 1 and Z can be 5. That gives us this environment. And A can be 1 and Z can be 6. And so that gives us this other environment. So in general, we have some environment that comes in. We use that to match everywhere possible. And some other environments, there may be more environments that come out if there are metavariables that are going to be inherited in the future. So now we go on to our last rule, and our last rule is not interested in A anymore. So we can take these environments and we can throw A away. We end up with Z equals 1, Z equals 5, or Z equals 6. But we do inherit B. And so then we have to go, like if we're thinking about this environment, we're thinking about this path through the matching process. We have to go back and we have to find out what was the value, or what are all the possible values of B at that point. So here we have Z equals 1 and B equals 4. It's more interesting in this case, because in this case, when A is 1, there were 2 possible values of B. And so we actually need to duplicate this environment like this and duplicate this environment like this. So the number, I mean, we can get the cross product of, or I'm not sure, it can explode a lot actually in some cases. So actually, there's no occurrences of I at all in our code, and so all of this environment is completely useless, actually. But it will go through each of them and see that there's nothing to do. So basically, there's sort of a balance between expressiveness. So expressiveness is like giving the user the illusion that all of these environments are maintained exactly as they are, and efficiency in the sense that we try not to duplicate any matching process based on the analysis of the metavariables that are actually being used. On the other hand, in practice, this mostly works out pretty well, but sometimes if you have a rule and it establishes some metavariables, and then those metavariables are used much later in your semantic patch, then you can end up with a really huge number of environments that are being maintained, and so you might want to reorganize your rules to use the metavariables more quickly. So there's a debug option, and then it will show you all the environments that are being maintained, and it can be quite easy to see that something has gone wrong. So the last issue is code generation. So basically our goal, again, is that we want the code that's not transformed to come back out in exactly the same way it was in the beginning. And so our solution for doing that is actually, we have our control flow graphs, and those control flow graphs contain abstract syntax trees, but ultimately everything is done at the token level. And so basically our tokens know about white space and all those kinds of things, and so by making the changes at the token level, then we can just sort of regurgitate the tokens that we have, and then everything comes out looking in a nice way. So we have a very simple example for that. This is a completely useless semantic patch, probably, that you take return E and we replace it by return. So this token level modification, it impacts both how the semantic patches are treated and how the C code is treated. So first, for the semantic patch, we parse the kind of code that's removed, and you can actually also in the semantic patch, I haven't illustrated that, but there could be some code that's not changed at all that just needs to be there for the matching process. So the unannotated code and the removed code gets parsed. We have an abstract syntax tree, and this abstract syntax tree is going to get transformed into a CTL formula, but this one is so trivial, this is just like a single node of the control flow graph, and so we just keep the abstract syntax tree the way it is. So basically we have a return expression, it has a return token, we have a metavariable expression, it has the name of the metavariable, and we have our semicolon. So that now we're done with the, we're not done with the semantic patch. We have to, what we do next is we incorporate the changes into this tree. And so those changes are also going to kind of float to the different tokens in this tree. So for example, basically we have these little minus annotations, because we're removing this entire line, then we go around to each of the tokens and we put a little minus on it. So whenever we do a match of that token with a minus on it, then on the C code side, that token is going to get removed. And we also have this addition of return semicolon. So the addition, we're removing all these tokens, so we could put the addition anywhere, but from a kind of management point of view, we find it easier to somehow put it inside the thing instead of before or after, and so we put it after this return. You can also put things before it would come up on the other side, but we're putting it afterwards. But basically now the abstract syntax tree contains all the information we need for the transformation process. So now we move over,
Can you say again, why does the semicolon move from one side to the other?
Why does the semicolon move from one side to the other? The
So
semicolon doesn't move.
Well, it looks like in the original code, the semicolon node is deleted and the semicolon appears, right, in the replacement on the left child of
Yes,
return.
okay. So this was just a choice. This is how I decided to write my semantic patch. Actually, you could ask this, the return is staying on the same side, but there's no real, in this particular semantic patch, there's no need to remove the return and add it back, and there's no need to remove the semicolon and add it back. So basically what happens is when you do a replacement, it just takes the entire thing that you replace and just drops it in somewhere. So It's not really moving. That's why at the beginning, I didn't understand your question at all. It's not moving. It's just getting removed, and then we put in return semicolon somewhere, but it's really transparent as to where it goes. It could have been put here, it could have put it here, it could have been put here. Makes no difference. Any other questions? Okay, so now we go to the C side. On the C side, we have our little function, and we do the lexer, and we obtain a string of tokens from the lexer. So I didn't feel like putting everything, so I didn't put the int main, that you should have tokens over here for int main, parentheses, and so on. But this is the interesting part. We have a token here. Here we have a token for the new line, and it has 2 spaces after it, because we have 2 spaces here for the indentation. Here we have our return. Here we have 1 space after it. Here we have 3. And this is an error. I should not have 1 space here because I didn't put 1 space here. So that was a mistake. We have a semicolon, we have another new line, and we have our brace. So this is our stream of tokens. We also parse it, convert it. When we take our tokens, we parse them, we get an abstract syntax tree. And then we convert the abstract syntax tree into a control flow graph. Here's a little bit of that control flow graph. But what I'm trying here to show here with the colors is that the abstract syntax tree embeds the tokens. Like this is shared data. This return node here is this. I don't know. It's an actual node. Contains lots of information. But part of that information is this actual token that's up here. So when we are doing matching over the abstract syntax tree, we can make changes to these tokens, and those changes will be reflected directly in this stream. So that's what happens next. Here we have our semantic patch. Here we have our control flow graph. This semantic patch, this abstract syntax tree is going to be matched against each of the nodes in the control flow graph. So we'll take that and we'll apply it against the brace, and that won't match clearly. And the closed brace, it clearly won't match, but this one here looks pretty much like that one. So we'll be matching. We start out with the returns. We go left and we see here we have a return. Here we have a return also, so that's good. And here we have some annotations. And so we're going to annotate this return with the minus and also with the plus. And so all of that information will go onto this return token, and it will end up here back in our token stream. Here we have a meta variable. The meta variable can match any arbitrary expression. It will be a big abstract syntax tree in principle. And so what's going to happen here, we have this annotation of minus. And so those minuses will go through all the tokens that are matched in that little bit of the tree. And then they will all get little minuses on it. And that, again, will be reflected up here. And the same thing for the semicolon. It has a minus, and so then a minus will get attached here. If the person had been silly enough to put this space here in the original code, what would happen is it would detect that we're removing the 3 and we're removing the semicolon, so we probably don't need the space in between them. And so there's a lot of transformations, pretty printing transformations to deal with things like that, kind of adjusting things, adding indentation when we have adding in complicated things and so on. And so this is the, still have this error here. So here was the token stream that we end up with, that we are replacing the return by everything, and then all of these spaces will ultimately get removed by this principle that if you remove something on both sides of a space, you don't need the space in the middle. And so then we end up with this as when we go through the remaining tokens, the brace, this one is still there because there's something removed after it, but not before. We make all these adjustments, then we just print it out what we're left with, and we get this as the output program that has the right indentation and spacing and so on. So the last thing is just the impact on the Linux kernel. It's been used, this is about when it became, we had something that worked pretty well, and we also made it open source somewhere around here. In the beginning, we ourselves did a lot of work where we submitted patches and we said, we did this using Coccinelle, just no particular suggestion that other people might do things, but we give an example of what we have done. There were also some very kind people who wrote some articles in some Linux kernel publications where they tried using Coccinelle and reported on their experiences and stuff like that. And so it kind of picked up over time when people started finding they had similar things that they needed to do. We have kind of other things to do, so we don't use it that much for contributing to the Linux kernel anymore. And other people use it more or less each year. So there's people who need to do large-scale transformations. There's also some rules that are in the Linux kernel, and they're run by bots regularly, and they find bugs or sort of some kind of out-of-date coding styles and so on. I mean, there's 9,000 reported uses. Maybe some people use it without actually reporting it. Some people, there's a whole effort toward hardening the Linux kernel, and they use Coccinelle quite a lot, but they might use it just for finding things and then make the transformations afterwards by hand. So it's kind of in the, kind of familiar usage tools of the Linux kernel community. So in conclusion, we have automatic program transformation, matching and transformation, making it accessible to the systems developer. It lets people do the kinds of evolutions they want to do, especially some kind of security impact issues. It starts to be even more important to make the changes. Independently of the amount of affected code. Of course, we still have to look through all the changes and be sure they're okay. We also have to get all the maintainers of all that different code on board with a change, which can be another challenge. There's a lot of discussion in the Linux kernel community about how that could be done better. I think it's a reasonable success in that we have thousands of patches that are in the Linux kernel where people have used it. And then on the research side, we have also some spin-offs. One thing we did quite early on was finding common changes so that we could find changes on which we could write the semantic patches and evaluate Coccinelle. That's a tool that has kind of lived on over the years. It's very patch parse. It's not really parsing the patches, so it can just work on the patches, and so it can be adapted to other languages as well. Spinfer, it tries to, now you have a bunch of examples, then you want to infer the semantic patch from the examples. It is able to do some things. It's not able to do everything that humans are able to do, though. So it's a kind of continuing research area. There's also the idea of semantic patches let you search for code and transform it, but they can also be kind of shifted over to be just a pattern matching language that you can use on the history. And so if you want to find complex changes that have been made in the past, then you can use that to kind of express them as semantic patches and search for them in your Git history. And we're also today working, we still maintain the C version, we're also working on C++ and on Rust. And so we have also some, as was highlighted in the previous talk, we have some positions available, either a PhD student or a short-term engineer, if you know anyone who would like to work in this area. So at this point, Coccinelle has been used really across the entire Linux kernel. So probably everyone attending this talk has used Coccinelle modified code in some way. Many of you, or some of you may use Linux on your laptop, so then you're maybe using it directly, but you're also searching for things on Google or Facebook and stuff like that. And all of these companies are using Linux at different levels in their infrastructure. So everything is publicly available. We have some very not super useful documentation on our website, and so on. So.
I have some time for questions.
Thank you very much, Julia, for the very nice talk.
Thank you.
So you mentioned the implementation of Coccinelle for Java, C++, and Rust. I was just wondering, what was the effort of porting Coccinelle for these new languages? And in general, did you also investigate of making Coccinelle more agnostic of any language by having an explicit binding to the language specification or something like this? Such as, for example, we can use it for any domain-specific languages.
Okay. Okay. So we have, yeah, I mentioned 3 languages, Java, C++, and Rust. So the Java version is a hackish prototype. I would probably not really advise using it unless you have some very simple things to do in Java. It doesn't really support modern versions of Java, and the parser has ambiguities that mean that it can't really parse certain things in certain ways. So there we basically just took the parser and tried to extend it. I think it's a separate parser, but it's basically the C parser that tries to get extended with some basic Java constructs so that it can parse some Java code. That's an effort that, I don't know. I mean, if somebody out there is interested in having a better version of Coccinelle for Java, then one might take a more industrial strength Java parser and try to hook it into our abstract syntax tree or something like that and get a better result. So an interesting feature of Java is that it's not preprocessor oriented, so you can actually use some kind of off-the-shelf parser. C++, on the other hand, it has the same problem as C. People write macros. And so we want people to be able to write their semantic patches in terms of what they see on the screen and not in terms of the macro definitions. There's also templates in C++, which add even more code generation complexity. And so for C++, we are trying to extend the C parser to handle C++ constructs. And so this is, if people are familiar with C++, it's like this really huge language. It's changing all the time. You have 4 million different variants of it. This is something that goes quite slowly. I have a colleague in HPC who's interested in using Coccinelle for modernizing HPC code. So some of this is in C++. It's a language that's relevant in that community. That code is like... it's entirely integrated, like the Coccinelle for C that you can download from our website or from GitHub or all of wherever. It has the C++ support built into it. Basically, if you want to add some new C++ construct, you have to modify the parser. Then you have to you make a new abstract syntax tree. You have to provide support for the abstract syntax tree. Coccinelle is organized as just like a generic, like a standard compiler organization. We have abstract parser, abstract syntax tree, and then we have a bunch of passes that do various things, and all of those passes have different cases for each abstract syntax tree entry. And then we come to Rust, and Rust is more like Java in the sense that Rust has a macro system built into it, but Rust is a modern language. It has a lot of tooling around it. It's not like arbitrary, strange things that you can do with C macros. The macro system is sort of a bit more integrated into the language, and the tooling, we use Rust Analyzer as our parser. We use Rust Format as our pretty printer, and so there we are reusing lots of existing infrastructure, and our implementation inside is very generic. Actually, the people, some like myself and an intern, neither of us knew any Rust before we started it, so we were not at all capable of writing a Rust parser or an appropriate Rust abstract syntax tree. The Rust Analyzer abstract syntax tree is nicely designed, and so we just use that infrastructure in a very generic way. On the other hand, it's like there we are using the same parser both for the actual Rust code and for the semantic patch code. Semantic patch code has some strange things in it. It has meta variables. It has ... It has the disjunction syntax. And so we have some kind of manual, not really manual, but like handwritten hacks to take the semantic patch code and convert it into something that can be recognized as our different constructs afterwards. So it's a bit of a hack to kind of lift the actual syntax of Rust up into the more abstract semantic patch syntax. But it's not really been a huge problem. So it seems like one could do something maybe with other kinds of languages, but we haven't really gone in that generic-ish way.
There were still some questions in the room, but we're running a little bit out of time.
Okay.
Julia will still be around for lunch and maybe later
Yeah.
as well. So please come and talk to her during the coffee break. And let's thank her for this inspiring talk.